This is Physics 1, Lab 5, Choose Your Own Adventure. I chose the falling slinky. Alright, so today we are comparing the predicted motion and the observed motion of a falling slinky. And you can see here our findings that they are very close, the model and the experiment. Okay, so our most important physics ideas are the velocity update formula and the position update formula, which is derived from Newton's second law. And we find VF equals VI plus F net over M delta T, and the position update as RF equals RI plus V average delta T. We also need to understand the gravitational force and the drag force. The gravitational force is your mass times the gravitational constant in the negative y hat direction. The drag force is the velocity squared times the direction of the velocity in the negative direction. Okay, so our glow script code. We initialize some properties such as the mass of the ball, the original position, and the original velocity, and we set our delta t to 0.04. We have to set our proportionality constant for the magnitude of the drag force pretty high because the video is in slow motion, so we have to account for that. We set our system as the spring and the surroundings as everything else. Here we put in the weight force and the force of tension. These are equal and in opposite directions because we need our F net to be 0 so that the spring will stay stationary during this loop. For the second loop, the tension force is gone and the spring starts to fall, so there is a drag force. So our net force is now the weight force plus the drag force, and that will change our velocity and position. Here is a video of the slinky falling. As we saw in the video, the bottom of the spring stays still until the top of the spring passes it, and we see that the top of the spring actually hits the ground first because of how fast it was moving. This is due to the fact that the tension force of the spring is equal to the gravitational force on the spring, so it stays in static equilibrium until the spring force goes away, which is when the top of the spring passes the bottom and it falls down to the ground. However, we must remember that there could be some sources of error, including issues with the camera being shaky and choosing the wrong spot as the point mass. Also, if the video wasn't super clear, that could also make it harder to see. Also, because the experiment was performed outside, there are variables that we cannot control, such as air resistance, but especially gusts of wind or other unknown factors. They are very, very close because it's straight at first because the y position is not changing while there is no opposing force, but when the tension force that is keeping the spring stationary goes away, it'll start to fall and the position will change. Why can we set the spring force equal to the opposite of the gravitational force? Because they are equal to each other in opposite directions because the spring is at static equilibrium. What if the spring had a greater spring constant? Well, then the spring would move up instead of staying stationary, like in our example.